The Doppler effect is when a wave experiences a change in frequency because the source of the wave and the observer of the wave are moving relative to each other. If you've ever had a police car or a fire engine drive by you as you stood on the side of the road, you likely experienced the Doppler effect. You may have noticed the pitch of the siren was higher as the vehicle approached you. That's because as the vehicle drove towards you, the waves got bunched up, creating a shorter wavelength and a higher frequency. And as the vehicle drove away from you, the wavelength got longer, creating a lower frequency. And remember that pitch is how the human body interprets sound frequency. Calculating the Doppler effect is actually quite easy. It's simply that the change in frequency over the original frequency is equal to the change in velocity over the original velocity. And by original velocity, we mean the speed the wave normally travels in a given medium. So if we're talking about sound, we're likely talking about the sound traveling through the air, and the original velocity would be 340 meters per second. The change in velocity is going to be the speed of the vehicle moving left or right. So if a car honks you on the freeway, a car traveling 60 miles an hour is roughly traveling 30 meters per second. And both of those equations are equal to the change of the wavelength over the original wavelength. While many people have experienced the Doppler effect with sound, you can also experience the Doppler effect with light. This usually occurs in astronomy. As a light source moves away from you, the wave gets elongated, pushing the wave closer to the red end of the visible spectrum. We call this a redshift. On the other end, if the light source is moving towards us, the light waves get bunched together, creating a higher frequency, pushing the color we see closer to the blue or violet end of the spectrum. Naturally, that's called a blue shift. If you've ever heard astronomers talk about galaxies or stars moving away from us or towards us, and wondered how you could tell a galaxy was moving, we can tell because of the color emitted from the stars. If a star is made of helium and hydrogen gas, we know the color that should be emitted. When we observe the star, if the color is slightly more red than it is when we burn helium and hydrogen in the lab, then we know the star is moving away from us. And if we observe the color to be slightly more blue than when we burn helium and hydrogen in the lab, then we know the star is moving towards us. Here's a fairly standard Doppler effect problem. We have a fire truck driving towards a crowd of people, and that fire truck is emitting a sound. However, because the fire truck is moving, the waves get bunched up, creating a higher frequency than would exist if the fire truck were standing still. So we need to calculate that change in frequency. Again, our equation is the change in frequency over the original frequency is equal to the change in velocity over the original velocity. Or in this case, the change in frequency over the original frequency is going to be equal to the change in velocity, that's the 5 meters per second, over the original velocity, which is simply the speed of sound in ambient air. Cross multiply and we get 2500 is equal to 340 times delta F. We divide both sides by 340 and we get the change in frequency is roughly equal to 7. Since the object is moving towards the observer, we know the frequency is going to be higher, creating a higher pitch. So the new frequency is simply 500 plus 7, or 507 hertz. This question looks just like our last one, with one minor difference. This time the question is asking about the frequency the fire engine perceives. So we're actually going to be using the Doppler effect twice. And that's because the waves get bunched together 2 times. First, as the fire truck drives forward, the waves get bunched together. When the waves hit the wall has no idea the fire truck is moving, so the wall bounces back the waves at the exact same rate. However, because the fire truck is driving into the wave this time, the waves will hit the fire truck at a slightly faster rate than when they were emitted. So we have to calculate the Doppler effect twice. We know from our previous question that when we calculated delta F over F being equal to delta V over V, we got delta F to be equal to 7, or the new frequency was 507. Now we do the exact same equation, this time using 507 as the original frequency. So our change in frequency that we don't know yet over our original frequency this time of 507, that's going to be equal to our change in velocity, which again is 5, over our original velocity, which again is 340 meters per second, or the speed of sound in ambient air. We cross multiply and we get 2535 is equal to 340 times delta F, or delta F is roughly equal to 7.5. So our new frequency is 507 plus our change in frequency of 7.5 to give us a final frequency of 514.5 hertz, or 514.5 complete waves per second.